Hey fam, this is also a different kind of video, and in today's video let's talk about the Sieve of Eratosthenes. Yeah, I know the pronunciation is a bit hard, but bear with me. Okay, yeah, this is a method used to find the number of primes, and it is like extremely efficient when finding the number of primes in a large given range. So how does it go? It was developed by a person called Eratosthenes very long ago in about 273 BC or something, and the algorithm goes as follows. What we have to do is to first we have to create an item called sieve, and in sieve we populate all the numbers from 1 to n, and what to do is for each multiple except one, for each number except one, we remove all the divisors of the number. So what am I talking about? Okay, let's see this example. Consider we have to find the numbers in range 1 to 100 and the number of primes in the range 1 to 100. So what we do, we create a sieve containing all the numbers from 1 to 100, and then one automatically we set to false or none, and then we start from the number 2, and we tell okay 2, there's a number called 2. So what we do is all the divisors of 2 we set to none. So 2 means 4, 7, in other words all even numbers become none. And then we go to 3 and set all the divisors of 3 to none. So 3, 6, 9, so on up till 100 they become none. And then we check for 4, but 4 is actually none. So what we do is we skip it, and then we go for 5, and again we set all the divisors of 5 to none, as shown over here. Every divisor of 5 set to none, which is 5 to 5, 10, 15, 20, so on up till 100. And then we go for 6, and 6 is actually none. So what we do, we skip to 7, and then we set all the divisors of 7 to none. But one thing we have to be careful is we should not set 7 to none. So 7, 14, 21, etc. So on till 100 they become none. And now what we see, the remaining numbers which are not none are all the primes between 1 to 100, and you can check it out, and it is actually true. I checked out twice just to be sure. So now okay, let's write the algorithm. Yeah, what does it take? It takes an integer n. So what we have to do, first we have to create the sieve. So and then we take an array and generate the sieve for the number sieve of n. So in other words, this takes the value n, and then for I in n, I add the position 1 if it becomes equals to and I'll tell you why it is I at the index 1. That is how I have taken it. Don't make mistakes like that where I wrote n instead of r, because you have to iterate through the array. And let's return the answer and the array. Okay, now so initialize all the elements before returning things. Okay, now so let's write the sieve. So what we have to do, first we have to create a two-dimensional array or one-dimensional array depending on how you take it, but I'm making it two-dimensional just to make it more clear. So what does array contain? The numbers from I plus 1, because we don't want the index 0, as we don't consider 0 while doing checking for prime and all. And let's actually set all the elements to true. In other words, initially let us consider all the elements from 0 to 100 to be true, meaning all the elements from 0 to 100 are primes. Okay, now what we have to do, the main thing we have to do is to set the array at index 0, in other words 1 to none or false at the index 0. And since it's a two-dimensional array and the second index is the true or false value, we set it to we set the first index to false. Okay, now initial steps are done. So what we have to do, we have to iterate through the entire array now and check for divisors. And there is one more optimization in this. The only thing we have to do is we have to check till the square root of the number which we have to check. For example, if the number given is 100, then we can just check till square root of 100. There is no need to check till 100, as within 100 itself all the numbers which are actually not prime will be removed. And this is the power. This is one way to write power in Python. And since the last index is non-inclusive, we write +1. The index 1, if it becomes equal to true, then what you have to do? You have to set all the other elements or all the divisors of it to false. So rather than individually multiplying all the elements from that from index I to the end, what we can do is we can just jump through the elements. In other words, I to the power of I, because if an element is prime, then what one thing which is guaranteed is all the elements till that the square of that number will also be prime. And this works mainly because we will have already checked for previous primes, and all the non-primes will be removed beforehand itself. And we jump in steps not of 1, but we'll jump in steps of I. In other words, all the divisors will be weeded out over here. And yeah, this is it. Now we can actually return ARR. And the shocking thing is, theoretically the answer should be done. So let me check it out. Let's check for 100. Oh, I forgot to remove the 1 over here. And yes, let me just add the index over here. 0. And yes, there are 25 primes, which are 2, 3, 5, 7, 11, 13. And yeah, this is correct. And you might ask, okay, why to use this when we can directly do the thing which we have been taught from when we were small, the brute force method. So just let me write that also, and we'll compare it till the integer n. And we take the value I, and if I is less than or equal to 1, then false. Or I hope you know how to check for primes, and if you don't know, then I really advise you to learn at least that. Yeah, again, this is one of the better optimizations of finding primes over there, where you just check till the square root of the number. If m modulo I becomes equal to 0, that means the number is actually divisible. So, or else true. Yeah, if the integer at index I is prime, then array dot append the ith value, and then brute force of 100. Let's first check if it's correct or not. And yes, we see that both are correct, and you might asking, okay, both are running relatively fast and all, so why do this? Okay, now let's check for some bigger number, like, okay, let's just check till 10,000, and I'll not return the array over here because it will just make the output look bad. And so let me run it as a run it as a code so that we get the time also. And it took okay, let's make it much more bigger. Let me not add so much zeros because it will take a lot of time. Run code. Yeah. Patience is a virtue and you have to have it. And yeah, obviously it took 7.639 seconds. And let me just copy this number so that my slippery fingers won't do any typos or wrong numbers. And let me just copy it over here and then run this as code. And yes, you obviously see the time difference. Okay, let me just return the answer over here. And again, let me run it as code to keep it consistent. And yeah, if you see the difference over here, 1.36 seconds versus yeah, it is taking too much time, much longer time to run, mainly because it's not efficient. Oh, it ran some wrong file. Yeah, no, brute force is running. Yeah, see, it took 7 seconds versus 1.3 seconds, and obviously, I don't think I have to teach math that 1 second is far smaller than 7.1 seconds. Yeah, so I hope you understood how the Sieve of Eratosthenes works, and you might be able to implement it somewhere, or even if they ask in interviews or stuff, rather than writing the most generic solution of this one, which everyone will know, and interviewer also will be knowing that okay, everyone will know this. If you write this, they will get impressed, obviously. So yeah, thank you. Happy learning.